here are two additional examples. They're a little bit tougher, so we'll start with the first one. A soccer ball kicked from the ground at a 55-degree angle lands 2.2 seconds later, and we want to find the maximum height and the initial velocity. So for our diagram, the ball leaves the ground, reaches a maximum height, and then comes back down. Speed lines, constant in the x, getting slower in the y, coming to rest in the y at the top, and getting faster in the y. Okay. For our given, we're going to draw the xy chart. We know that the angle is 55 degrees and the time is 2.2 seconds. So I'm just going to write those in the middle since those apply for both. So t equals 2.2 seconds and theta equals 55 degrees. The nice thing about these angles is the angles are always relative to the x, so you don't have to worry about subtracting 90 minus the angle ever with projectile motion. What we do know in the y is that the acceleration is negative 9.8 meters per second squared, and we do know in the x that the acceleration is 0 meters per second squared. And we have one other thing that we can know for the y. The soccer ball starts and ends at the same height. So my delta y for the whole time is going to be equal to 0. Okay, so what are we looking for? We're looking for the maximum height, so we're looking for delta y max. And we're looking for the initial velocity. So we're looking for the initial velocity. I'm going to put that in the middle because, again, it's not x or y, it's a combination of the two. So now based on what we're given, we know the time. The time applies to both the x and the y. We know the angle. That also applies to both the x and the y. So in the x we can say that we know time. In the y we can say we know time, we know angle, we know angle. And I'm just writing those there, but they're fine in the middle. So given in the x only time, you're not going to find much of anything yet. Given in the y, we have an acceleration, a delta y, and a time. I can use an equation given those things. So since we're going to start in the y, let's look in the vertical, and let's look at all of the motion. Delta y, time, acceleration, it's going to make sense to use delta y equals 1/2 a t squared, since we have those three things, plus v initial y t. My only unknown in here is the v initial y. Delta y goes to 0. Rearranging for v initial y, we get negative 1/2 a t squared equals v initial y t. That t goes away. So negative 1/2 times negative 9.8 meters per second squared times 2.2 seconds equals v initial y. Multiplying this together for v initial y, we get 10.78 meters per second equaling v initial y. So we're looking for delta y max, and we're also looking for the total v initial. Okay, so now that I know v initial, I know my time from start to finish, and I know what my acceleration is. I'm going to look at the vertical, and I'm going to look at up only. So looking in the vertical, up only. Again using delta y equals 1/2 a t squared plus v initial y t. Looking at vertical up only is going to let me figure out what this maximum height is. But if I'm only going halfway up, I know that my time for the way up is going to equal 1/2 of the total time. So half of 2.2 is going to be 1.1 seconds. Delta y max equals 1/2 of negative 9.8 meters per second squared times 1.1 seconds squared plus the v initial I just found, 10.78 unrounded meters per second times 1.1, I'm out of room, seconds. Multiplying all of this together, we get 5.929 meters. 2 sig figs, delta y max is approximately equal to 5.9 meters. Now the last thing it's asking us to find is our v initial. Again, I'm just going to use the vertical. I already know what v initial y is, and I also know that v initial y is equal to v initial times the sine of the angle. So v initial y divided by the sine of the angle will give me my actual initial velocity, 10.78 meters per second, divided by the sine of 55 degrees equals v initial. Dividing those, we get 13.15, keeps on going, meters per second. So my actual initial velocity with 2 sig figs is approximately 13 meters per second. We did not have to use the x at all for this problem, and that's okay. We could have used the x, but I chose not to. Again, you don't always have to use the same equations. I could have used a combination of a couple of equations to figure out different things. I used what made sense to me. You can use what makes sense to you when it comes to solving. I'll do one more example, again a little bit tougher, and then we'll do more practice. Okay, in the last example, a pitch ball is hit by a batter at a 45-degree angle and just clears the outfield fence 98 meters away. If the fence is at the same height as the pitch, find the velocity of the ball when it left the bat. So we've got a ball leaving the bat, it's going up, and then it's coming back down and just clearing the fence. And the fence is at the same height as the height the ball was pitched from. So constant velocity in the x, slowing down as it goes up, speeding up as it comes back down. If we make our xy chart, we know that the acceleration in the x is 0 meters per second squared. We know that the acceleration in the y is negative 9.8 meters per second squared. It tells us that the angle is 45 degrees. I'm just going to put that in the middle. So theta equals 45 degrees. And that the fence is 98 meters away. So my delta x is 98 meters. We know that the ball starts and ends at the same height. So delta y is going to equal 0 meters. And we don't really know anything else. But what we're looking for is the velocity of the ball when it left the bat. So what we're trying to find is my v initial. So now based off what we're given, we're going to have to decide whether we want to work in the x or the y. It's going to make more sense to use y. So we're going to look in the vertical. Using delta y equals 1/2 a t squared plus v initial in the y t. My delta y is 0. So negative 1/2 a t squared equals v initial in the y t. T goes away. So negative 1/2 a t squared equals the v initial in the y. Now the fact that the ball was shot at a 45-degree angle means that my x velocity, initial, again, x is constant, so initial x is the same as final x, but my initial x velocity is going to equal my initial y velocity. And that is only because for this problem, theta was 45 degrees. So v initial y equals negative 1/2 a t, that should be t, not t squared, equals negative 1/2 a t. And this therefore also equals my x velocity. Okay, so in the vertical, we know that negative 1/2 a t is now, and this is a y t, is now equal to my vx. Looking at the horizontal, the only equation I know in horizontal is that delta x equals vxt. So delta x over t will equal vx. I've got two expressions now for vx. I'm going to set those equal to each other. So negative 1/2 ay t equals, that should be a delta, delta x over t. Negative 1/2 ay t squared equals delta x. We know delta x, we know a, so let's isolate t squared. T squared equals delta x over negative 1/2 ay. So t squared equals 98 meters divided by negative 1/2 of negative 9.8 meters per second squared. T squared equals 20 seconds squared. So taking the square root, my time is equal to 4.47, keeps on going, seconds. Now that I know the time, I can go back into the horizontal. We're looking for my V initial. So going back into horizontal, delta x equals Vxt. So delta x over time will give me my V initial in the x. 98 meters divided by the unrounded 4.47, keeps on going, seconds, equals Vx. And this number is 21.91, keeps on going, meters per second. Almost done. You know that V initial in the x is going to equal V initial times the cosine of the angle. So V initial x over cosine theta equals V initial. 21.91 keeps on going, meters per second, divided by the cosine of 45 degrees is going to give me my initial velocity. And that number comes out to 30.99, keeps on going, meters per second. 2 sig figs, so V initial is approximately 31 meters per second. And that's how you would solve this one. So again, not given much information at all. The only real numbers we had were the delta x and the angle, but using a little substitution, we were able to figure out what that initial velocity was.